This is the root test by Zoe Flavin and Mitchell Finkel. In the root test, we suppose that the limit as n approaches infinity of the nth root of the absolute value of a sub n equals L. If L is less than 1, then the sum of a sub n is absolutely convergent. If L is greater than 1, then the sum of a sub n is divergent. If L equals 1, then the test is inconclusive.
It's Mitchell.
Now we're going to show you an example of the root test.
Here's Zoe Flavin.
So the root test is really good to use when you have like an n degree, either in the denominator or the numerator. So here's an example we're going to do. So the sum from n equals 1 to infinity of n squared plus 1 over 2n squared plus 1 to the n. So when you see the n in the exponent, it's a good sign that you should use the root test. So then you do the limit as n approaches infinity of the nth root of the absolute value of a sub n. So then you plug in a sub n into this. So the limit as n approaches infinity of the nth root of the absolute value of n squared plus 1 over 2n squared plus 1. And you know that this is always going to be positive because anything squared is always positive. So you can remove the absolute value signs. And then, so this is to the n, sorry. So you know this is always going to be positive because n is always going to be greater than 1. And then the nth root of n removes the n sign, and you just have, or the n exponent, and you have the limit as n approaches infinity of n squared plus 1 over 2n squared plus 1. And because they're the same degree in both the numerator and the denominator, the answer is 1/2. And so, then 1/2 equals L. And as Mitchell said earlier, if L is less than 1, then it's convergent. So that is how you tell whether a series is convergent or divergent using the root test.